So thank you so much for inviting me, Mikael. Like you said, I run a company called Scaleout. I don't know if you have heard about it, but it's a spin-out from our research environment in Uppsala University. We've been at it since about 2018, building technology slowly, and we're doing something called Federated machine learning that I'm sure some of you have heard about, but maybe not looked at depth into. So it's a quite new approach. It's a very active area of research in academia, and a Scaleout where we're building a software framework essentially for enacting federated learning in various situations. And the problem that we are interested in when we consider federated learning is that we observe a lot of barriers for machine learning if we go and look in the enterprise primarily. And it's related to data sharing, so data movement. So we can, if we have data that is generated or created at various geographically distributed or siloed locations, could be vehicles, could be on smartphones, it could be in data silos in large enterprises, different teams, different subsidiaries, and so forth. We encounter this barrier. So one of them is we think of as we cannot move data. So in this category, we see a lot of edge computing applications where we see practical blockers. This is essentially the big data problem on the edge, that it's hard to transfer and stream data over low quality networks from, for example, a vehicle to the cloud or to an HPC cluster. We have also this category, which is a big one that we think of as not allowed to move data, where we essentially have regulated data sets. This could be GDPR, sensitive personal information on smartphones, for example, or medical data is of course an example there. So, but also data transfer laws. So it could be a company having subsidiaries in different parts of the world, where there are like legislation that prevents movement of data across country borders. So China, Europe is one such example. And then we have also a fairly big category, which is simply we don't want to move data. It could be that it is sensitive, maybe not regulated, but it's business sensitive. So this could be, for example, a software developer. Maybe they have a hardware or and a software offering. So maybe they're selling, for example, I don't know, microscopes to a hospital, and then you have software on top of that you want to make smart with AI features. But the customers, they are owning the data that you need to train it. So that's another example of those customers may not want to share that with you as a system developer. And then federated learning is an approach there. Also, in general, cybersecurity, that there could be reasons for not creating copies and moving data around unnecessarily, just in order to improve cybersecurity. So it's something called a copy problem. That occurs when you essentially create copies of data. So yeah, for all of these reasons, it can sometimes be hard to progress machine learning projects because you can't pool the data in a central cloud. So I'm just going to give a few examples before we dive into federated learning. So one case that we worked on early is a collaboration with Scania Connected Vehicles, where the objective here is to push learning to the onboard computer. So this is an R&D customer of ours. The main motivation here is this kind of large quantities of sensor data that you might want to learn on before it's deleted or stored. And if you can then apply federated learning, you can create this kind of fleet learning effects across a large quantity of vehicles. A related case, but completely different and much simpler software stack is a smartphone. So there we also have a project we're working on where we want to enable machine learning training in a mobile application that needs to use data from the end user that can be sensitive in order to improve certain machine learning models. So that for this reason, for example, we developed an Android SDK recently to do this. So here, federated learning can also kind of create this fleet learning effect. Typically, users will not have or generate that much training data on the device, but by sort of the scale of things, you can still hope to achieve good models. Third one that I think is a bit interesting is also something you typically maybe think about when you talk about federated learning in the media, and this is kind of cross-organization collaboration. So one organization called Eurocontrol, they're an agency that are working with air traffic management in Europe, and they also have an innovation department that is trying to do things better with machine learning, for example, slot time predictions at airports. But the data you need to improve models can be then owned by different airlines, for example. So Eurocontrol is then trying to set up some sort of machine learning collaboration where they can actually process data from different airlines in order to improve models. And then federated learning is one such approach that you can apply. But how does it work then? And I should also say, at any point, just stop me if you want to ask questions. It's easiest if you then just unmute and tell me what you want to ask. But federated machine learning then, it's a distributed approach, as you have understood. It's about processing on device or on silo. And all federated learning schemes, and there are many varieties, of course, they fall on this same pattern, at least what we call horizontal federated learning. So we have, instead of pooling the data, sending the data to central storage, we start with a centralized central model or a global model we typically write in federated learning. We extract parameters from this model. If it's a neural network, it's weights and biases. We send them or distribute them in some way to the clients where the data resides. We compute small updates to the model, and then we send parameters back, never the data, just model parameters back to the server, and then we aggregate them in some form. And then we have done like one global round of federated learning, and then we repeat this until convergence as usual. So it looks very much like distributed machine learning, but I will elaborate why there are like unique challenges in the federated learning setting. But yeah, like I said, there are of course a lot of research done on how specifically would you aggregate models, how do you try to make communicate as little data as possible in every round to make it efficient. All of this is like quite large areas of research in academia. But I wanted just to show you what it could look like. So the most common algorithm still for averaging these models is something called federated averaging. It's essentially you just compute a weighted average of the parameters that you send back to the server, and they are weighted with the number of training samples that you have on the device, or that you have done in that sort of parameter update. So it's a quite simplistic setting, but it kind of works well in many cases. But like I said, there are several or a lot of different flavors of this that you can apply if things don't work as expected. But in simplest form, it can be as simple as this. Yeah, so taking a step back about Scaleout then, so what we're doing, like I said, we're developing software for creating such federated learning setups in various contexts. So in that sense, we sort of work on the intersection of, I would say, machine learning and security. So this is a way we think of this as a way to improve cybersecurity in machine learning pipelines, essentially, where data is distributed. But what could you hope to achieve with federated learning? So that's, of course, like an important thing. And we made this figure a few years ago to illustrate this, and several groups have done similar studies. There are plenty of them. So in this case, we looked at the performance of federated learning training versus centralized training. And in order to do that, you of course have to start with some sort of public data set. So in this case, it was a cancer image data set that has been anonymized. It's been used for research. It's about classification of blood cancer cells in different stages. So it's a multi-class classification problem. We solved that using CNN. And then in this figure, what you see here is then the orange curve is when you take the full data set, centralized, and train as usual. And then the green curve is with this federated averaging algorithm, when we have split the data and emulated 10 different hospitals. So we have created like 10 partitions. And then you can, as you can see, then federated learning achieves essentially the same performance as the centralized training, but you have a little bit shaky convergence initially, and this is quite typical. I mean, there's like a little bit slower, typically a bit poorer convergence in federated learning due to this distributed training nature. But over and over again, you see that you are able to recover the same or better performance as you have from the centralized model. But the blue curve is perhaps even more interesting, because that's the one that you would compare to in a real world situation where you can't pull the data. Because remember, like we're doing federated learning because we can't have a centralized data set. It doesn't exist. The blue curve is the best model we could train on a single data set or a single emulated clinic in this case. So we also, of course, want to see that we are able to get a stronger model than any individual or the individuals can do in isolation. So that is typically an objective also of federated learning. But that doesn't have to be the case always. I mean, the goal could also be to create a model that generalizes well and that has lower bias by seeing more diverse data sets. And then you can, of course, fine tune that as usual for your local data set if you want. Take away there, federated learning, distributed setup, where you send parameters to clients. They have their local data, they compute small updates, that gets streamed back to a server, which aggregates it. And if everything works as it should, and you set up the problem correctly, you get in with the same model with federated learning as you would have gotten if you centralize data and train centrally. The price you pay is now you have a distributed system that can be quite complex. But on the other hand, you have strong privacy enhancement in your machine learning pipeline. Just simply because you don't share data, so that whatever security perimeter it is around the individual data sets is still in place. And as such, I mean, we at Scaleout, we really believe that this is like a future cornerstone technology, particularly in edge computing and fleet intelligence, where for various reasons you can't really.
Andreas, we have a question from
Andreas.
Andreas.
Yes, so interesting. So now you split to 10 hospitals, but if the source would be something like a mobile phone, is there also a problem where these small batches become too small? Like, is there a way to express when the federated learning breaks down because you have too many hospitals and too small data sets? I mean,
probably that, and I think it's like on a case by case basis. So that could be related. Yeah, maybe you could envision situations where you have too much noise in the gradient updates locally, that you get problems with the overall convergence, if that's what you mean.
Yeah, I was wondering
and
if
then
people have done this kind of experiment to measure at what point the federated strategy breaks down. If I would split to 100 hospitals, 1,000 hospitals, at some point, I guess it would not work so well. Or do I misunderstand?
No, I think it in principle it could work, but it could be that you have to then increase the number of communication rounds as well. Because in the limit, you kind of recover in the limit of very small updates on the clients. You could see it as you recover essentially parallel SCD or parallel Adam, more or less. But yeah, there could be a case, of course, where the batch sizes become too small. But no, not systematically. And I don't think one can do it generally, but one can do it certainly for a certain use case. So in fact, I will look at this. I'm setting up a large-scale cross-device simulation testbed as we speak right now in one of our Vinnova projects. I will definitely run some experiments, but I think there's going to be in many practical ways to make sure that it converges. One thing, of course, that is a bit more tricky in a federated setting is like the hyperparameter tuning. First of all, you have some related to federated learning, and also it's not very practical to do do as you usually do. So that can be a challenge, I think. Yeah, and now we talk about this. We can quickly talk about this. Well, we're talking about two different use case categories. So we call them federated learning cross silo versus cross device. So what I talked about in this picture is a use case, typical cross silo use case, where we envision maybe that the number of clients are like in the orders of up to 100, and typically local data sets could be expected to be fairly large or reasonably large as well. Versus in the cross device, we're targeting installations where we need to scale to millions of devices. I should say also that this one here I show because in this case we have a centralized data set. We have progressed this quite nicely with a group at Linköping University. It's in a project called Assist. So we actually have now up and running training with our software for 3D brain tumor segmentation with units on 3 of our university hospitals. And I don't have results yet, so they are still running a lot of computation. But in that case, we don't have the centralized comparison because you can't make the pool data set. Essentially, you can't share the patient data. But soon, at least before summer, we should have a federated trained model for that scenario, and it's going to be expanded with 3 or 4 more hospitals, hopefully, in the spring. Yeah, I just wanted to cover briefly, like in federated learning, of course, then we have this kind of need to distribute models and aggregate models. And you can envision different ways of doing this. So this is essentially the distributed computing aspect of it. So in the most typical setup, you would have like essentially an all reduce where you have some server, you distribute the models to all the clients, and the clients share the models back to the server, which aggregates. This is what we talked about so far. And I think this is the setting that is practical today in industry settings that you can actually implement in a reasonable way. But I should also mention that there are, of course, people that are pursuing in research other modes of doing this in an even more decentralized manner. So you can do this, for example, with different peer-to-peer strategies, trying to make the coordination of computation decentralized as well. And it has certain advantages regarding the potential to not having to have a trusted third party for the aggregation. But there are severe scalability challenges. But that could be interesting to be aware of. That this is, of course, an area of research as well. So if you're a computer scientist, I mean, you can think of doing things like gossip protocols and other things to aggregate the model at scale. But yeah, since we are a group of data scientists in this seminar, I also wanted to talk a bit about what are the challenges then? And one thing that is frequently studied in federated learning context is what we think of as statistical heterogeneity. Because as you can imagine, since we have no control over how the data is distributed across clients, we should expect that the data is not IID. Even in this case of hospitals, for example, there could be different calibrations of image acquisition experiments. There could be doctors labeling in slightly different ways, so that data can be a little bit out of distribution. You can also imagine quite unbalanced the settings where a couple of clients maybe don't have training examples from all classes in a classification problem, or quite unbalanced data sets in terms of size. All of this, of course, in combination with the fact that we need to do fairly large updates and large, in some sense, maybe an epoch or a couple of epochs on local data set in order for the communication to be practical, since we need to communicate over internet, could cause challenges. So this example just illustrates this is a very exaggerated example where we took Cypher 10 and progressively made more and more malignant partitions, where in the blue curve, the worst case, each client only sees examples from 3 of the classes. This is the Cypher 10 class classification problem. And as you can see, then you might run into issues if you do things naively with federated learning. where you don't converge, essentially. And this, of course, it would converge in the limit of single updates on the clients, but that's not practical from a communication perspective. Yeah, so that's one area where people are looking into, like, how do you handle this, and then there's this research into different type of aggregations and weighting strategies comes in. So there's ways to handle this. Another one that is quite prominent is that of system heterogeneity. So as you can imagine, if you have a federated learning setup, even with smartphones, there will be variations in the hardware that will lead to variations in how fast the client can compute an update, for example, which could lead to a problem like, for example, that some clients will update out the round or try to update the model later, so forth. And then, I mean, do you wait for those, or do you need to have some sort of deadline in a global round? Otherwise, you will have to wait like for the slowest client every time. So that could mean that you need to do things to handle the fact that clients we call them stragglers, can update late. And that may or may not impact the convergence as well. And also, again, there are a lot of work done on how do you handle this with different aggregators. Typically doable. A related problem, more from a system side, is more of a practical problem that you have to handle system. I mean, you have to be very resilient to failure. So you can expect to see that clients will connect and drop out of a federation many times or frequently. Sometimes because the connection is poor or there's a failure. And I mean, imagine a truck, for example, that goes into like a low connectivity zone. But it can also be a mobile application where you can't have it on all the time. So it will maybe pop up for a few minutes, participate in training, and then shut down. So this figure illustrates this. Like if you have here, there are different global rounds, like one iteration of going out, updating, coming back. And the green and pink curves here, they kind of illustrate that clients can start in the middle of a round and drop out in the middle of a round and things like that. Nothing fundamental, but still, if you need to build a system for this, it requires care to make sure that it's resilient. And then another obvious challenge is scalability, both if you want to run large models on cross-silo situations, but in particular, if you have the cross-device situation, you need to scale to a very large number of clients. So if you have this kind of typical client-server setup, you can have the server can become a bottleneck, of course. Weak connectivity can cause communication bottlenecks. Coordination of computation could become a bottleneck, in particular for cross-device. So obviously, this is also something that you need to handle in production-grade federated learning. So for all of these reasons that I mentioned, this kind of challenges, I usually say then at this point that federated machine learning, it looks like distributed machine learning, but it's not really the same. And I think the key difference is that if your goal is to parallelize machine learning training, you still have a centralized storage, typically, or a shared storage. At least if you do like now I'm thinking mostly about data parallel training. But you have some control over how you partition the data. You can load balance. You can make sure that it's optimal from a class distribution perspective, things like that. In federated learning, we have no control over this. The data will be whatever the data is at the client side. And the other thing is, of course, that like it's very different doing this over the internet with this kind of heterogeneous devices than doing it in a supercomputer with the infinite bound network and I mean the very reliable compute infrastructure essentially. So there are like differences there. And what we do with Scaleout then, well, as I'm alluded to here, bringing this technology to production, which is our ultimate goal, both that to see that enterprises actually create value from this. And that we can do it practically. It will require from a software framework. I mean, we need to be scalable. We need to be resilient. We also want to be agnostic to the federated learning runtime. So we need to build a system that has all these properties. It has to be secure. We have to be able to operate it also. I mean, it's not just that we build it, but it has to be able to run in production by without like too much effort. And then, of course, we're going to need to integrate with a lot of different systems, both like existing central MLOps tool chains. So like this essentially can replace the training step in a pipeline, but it needs to interface with all the other stuff, serving and monitoring and whatnot. But also on the client side, like on the phone or in the truck, we need to do API integrations with other components, OEMs, systems feeding data and so forth. So that's like quite something that needs to be thought about. And then, especially for this cross-device or cross-collaboration case, this also needs to be like solutions in place that enhances trust and lets you govern these type of collaborations. So this is maybe the area where we have done least work so far, but that we're continually progressing on the pipeline. So in Scaleout, or this also comes from our lab, we started off with an architecture for federated learning that addresses scalability and resilience in a good way. So unlike most research literature you read, our work built ground up, based like inspired by MapReduce essentially. Has nothing to do, like no similarity with implementation, but instead of a single server, we built a tiered architecture from the beginning, so that we assume that our aggregation servers are more or less stateless and that we can replicate and scale them horizontally, both geographically or within a cluster to load balance. So each of these combiner services, as we call them, they have responsibility for a group of clients, maybe 1,000 clients, or if it's a cross-device situation. And during a round of training or some rounds, they sort of have independent responsibility of coordinating updates and aggregating them. And then on the top level, to form a global model, we then do another round of aggregation or reducing to combine models from combiners. With this said, I mean, many early use cases, they can do well with just a single combiner in this kind of traditional client server setting. But this architecture means that we can scale this very broadly to millions of devices. And this is also something that we will do in a case study quite soon. And then another sort of thing we have done or worked quite a bit on in Scaleout is this kind of making sure that we can monitor things, that we have tracing so that we can debug situations when it's inherently hard problem to debug things in distributed systems, that we can audit and trace what has happened during the computation, which clients reported models when and so forth. So it's a little bit more production ready than other open source alternatives. Discovery services and then handling client authentication and so forth. So this we implement in a Apache 2 framework called FEDn. It's a Python framework on the server side, and on the client side, it's language agnostic, so you can implement clients in any language you like for the integration, like with the machine learning code and the data, essentially. And then we build to complement this SDK, which you as a developer, if you're a good developer with DevOps skills, you can use this and deploy your own like distributed federated learning settings. We also develop a solution called FEDn Studio, which is part of our enterprise suite, where we provide one such managed or production ready deployment of the server side components with on top of Kubernetes, essentially. So that requires a Kubernetes infrastructure, a vanilla one. And here we also then add, features for managing clients so that you can generate or issue tokens, like tokens for clients so that you can manage their identity and security. Things like this, some collaboration features as well. And then we're on our roadmap, we have more and more like things related to like integration with this MLOps pipelines and stuff like that I mentioned. So that's about that. Follow cloud native practices when we design the software. So like FEDn, like I said, something you can just work with if you're a developer. And then if you want pre-baked sort of or production-ready deployments and UI experiences, then you can use FEDn Studio. Yeah, so I'm kind of like wrapping up here, but I also wanted just to say that if this is of interest, like if you have a person interested in learning more, there's a workshop every month where you can bring your laptop and be part of a federation with us. Yeah, you can also have, you know, accounts. We run this studio software as a SaaS for pilots. It's a shared environment. It's not suitable for IP sensitive models, but it can also be used just to play around and do things to learn about federated learning and do quick POCs. So that's also available, even for free. And then, yeah, exactly. So this is a bit what we're doing with Scaleout, trying to bring this technology to market. Can I have 2 more minutes, Mikael? Is that okay?
Yeah,
We
absolutely.
started a bit late. Yeah. So I just wanted to take a step back then and look at, okay, but look at the privacy landscape for machine learning. So this picture illustrates this landscape from something called a UN Handbook for Privacy Preserving Techniques. And we talk about 2 main things when we talk about privacy: input privacy and output privacy. So input privacy, that is about what can you learn about the input data during the process of computation, so during federated learning in this case, by essentially directly accessing the input data, training data in this case. And then there's something called output privacy, which is more about what can you learn about the input to the computation after the computation has happened. So in the machine learning context, this becomes if you have access to the trained model, for example, what can you learn about the input data? So this is about attacks and reverse engineering of the data by, for example, access to an API inference endpoint. And in the federated learning context, you have access to the model on device. So federated learning in this privacy enhancing technology landscape is a technology that is designed to address input privacy, simply by making sure that the data never moves, the data stays local. So that's like the most fundamental approach to like protecting input data. Then, of course, there is a lot of research done or work done also in the output privacy set case where you look at sort of attacks on these type of systems. So we are involved in several such projects, led by us or by, we're involved in one with AI Sweden, one with Uppsala University, where we look at machine learning, and federated is usually our angle, but for machine learning in general and cybersecurity. So LeakPro, for example, aims at doing a test bed for attacks on privacy attacks on machine learning models, both in a centralized API serving setting, in a synthetic data setting, and in a federated setting. So that's also maybe interesting to know about. And then for the output privacy, you can combine federated learning with other technologies like differential privacy, various forms of special forms of encryption called homomorphic encryption, and other approaches as well, depending on the needs in your use case. Yeah, and Scaleout as such, we're not finished, it's work in progress, but we're looking also like a lot at the security of federated learning, trying to sort of think about how there's something called the OWASP standard for web applications, web services, that looks at sort of what are the top threats against the systems. People have then translated this to MLOps to think about what does this mean in an MLSecOps setting. And we at Scaleout will also think into, working on, okay, but what happens, what additional things do we need to care about when we then go to a decentralized MLOps setting. But we're not finished, it's something that we continuously work on. Yeah, team, we're about 10 people, located in Uppsala, Stockholm. We have one office at Söder and one in central Uppsala. You should come and visit at some point if you are in the neighborhood. Yeah, thank you. That's it.
Thanks a lot. Super interesting presentation. Yeah, the floor is free for questions if you have any. I can start. So I have a couple of like meta questions, I guess. For example, I haven't heard that much about other companies focusing specifically on federated learning. So what does the competitive landscape look like globally?
Globally, I mean, there are a bunch of, or a handful of, order of 10, I would say, serious startups that are looking into it. The most prominent one that we are usually compared with is called Flower Labs. They're more like research-oriented framework, quite popular in academic circles. Doing more like of a open source community project where we're doing more open source collaboration with enterprises. I mean, of course, it's open source in any case, but yeah, there are a couple in the US also that focus on, but they have recently started to focus more and more on federated LLMs, things like that. So we are a little bit more focused, I mean, horizontal and maybe even more towards mobile applications and edge. Yeah, so, and then I think all the major enterprise, like the big ones, IBM, HP, NVIDIA, they also run essentially research groups that look at federated learning. Some of them have frameworks as well. They are, of course, doing it mainly to create interest for edge hardware solutions, things like that. But they are usually quite good. Yeah, so there are a couple of open source frameworks, including ours, and then so forth. But in the Nordics, we're quite alone with this, and this could be a reason why also you don't really hear so much about it in that setting. But yeah, so yeah, a couple of startups globally that look into it.
Okay.
Yep.
And I don't see any more questions, so I'll continue. So, and I can.
Well, sorry, Mikael. Since I know you're from life science, I just want to comment. I mean, maybe you've heard about a company called Oaken. Like a medical AI company. So there are also some of them that are like vertically focused, like looking at medical images, like medical health data, for example, that incorporate federated learning in their offering, but where the main offering is like, consulting services and software for medical AI, for example. So there are also like those examples.
Right. Yeah, that goes a bit into my next question. So it's quite easy to imagine that this is interesting for medical applications, and indeed I've heard it many times from people that they would like to try federated learning for that. But what other application areas are sort of active, like are showing a lot of interest towards federated?
Automotive, I would say. So that's maybe the area where I think we have. I mean, it is early technology, so we're quite stubborn in this way. We know it's early and we're going to bring it to production. But I think automotive sector is looking into it quite heavily, both in R&D and also we see, like, for example, the work we do with Scania, things that are actually progressing to something that looks more like real world as well. So that's and then the main driver is the combination of maybe fear for future regulations and privacy things, but also like this big data problem. But in general, I would say IoT, industry 4.0 is like interested in it. Yep.
Yeah. Gino.
Yeah, hey, thanks for the very interesting presentation. I don't have much of a question. It's more of a reflection. Sorry, I hate the person that usually comes up with this kind of commentary in talks, but I'm the kind of person right now. I work, a little bit of background, I work at Socialstyrelsen, National Board of Health and Welfare. We have a lot of data, very sensitive data, and my job here is to provide researchers with parts of this data pseudonymized. We don't, yeah. So you understand the concept of pseudonymization? Yeah. And we are many people doing this because there's a lot of requests, lots of work. We are always running behind. So, and we have gigantic queues of researchers like waiting for months for data because it takes a long time to do the sekretessprövning. We have to check that they need the data that they are requesting, and that they have support for that in the ethical application. And once in a while, when we discuss how much work we have, somebody comes up with the idea that, oh, but maybe if we use federated learning, if researchers use a federated learning scheme to, against our data, then we have less work to do. And I wonder if that's the key. Like, my picture of it is that wouldn't be the case. Like, because maybe it's less work to do with the sekretessprövning, because we don't have to check that we're not leaving out data. We don't have to check that they need the data that they are requesting. But like, often, like, we would need to massage the data into shape that kind of fits with the requested.
You mean that you need to do their pre-processing?
I need to do the pre-processing, and usually data looks like shit, so it takes a lot of time. So that part, right? It does, that part doesn't go away, but
that part doesn't go away. I mean, yeah, that's a good point, and one we often gets asked, yeah, it doesn't replace solid data management principles, of course.
Wow.
But I also say it's usually not. I mean, it's not really harder in a federated setting than it is in a centralized setting. But yeah, you need to like control of your data, because as always, I mean, the client updates, they need to read the data and pre-process it, format it, whatever they need to do, and run the training. So that part is no different.
Yeah.
You need to load it in memory and fit the model to it. So that part needs to be in place. What can be, of course, a bit harder in federated learning setting is that there needs to be some sort of collaboration happening in this case, so that everyone knows what the data looks like. If you ship the data to them, I mean, they can reformat it themselves. And they can do this so the way we solve it in FEDn is that we have this option that you, essentially as a data scientist, you create a code bundle, we call it code package, with entry points that tells the framework what do I need to do to compute the training update, what I need to do to the validation update. And as part of that package, you can of course put ETL and pre-processing stuff, or typically you do. So you can push that out to this as a data scientist working with our platform. You develop this, and it's good if you have some sort of it, but that could be synthetic, like a little bit of data that you can work with locally just to debug the scripts. But then when you've done that, the framework will push it out and enact the computation on the data set. And of course, that becomes easier if you have data that is structured. And maybe this is also why we're seeing, more maturity in the IoT case, where data is generated by machines, sensor data. But in your case, I mean, do you have multiple data sources, or do you have like one data source, and the challenge is you can't share it?
No, we have a whole bunch of data sources. We have 20 registers, of which, like, some of them, many of them are not consolidated in one data set. They have,
exactly.
So it's a mess.
That's actually one good point is that your colleagues have done. I mean, what you could do if you have, if all of them are different, I mean, it will be a lot of scripts, but in principle, you could bypass. So usually what happens with organizations that end up in this situation is that they start like a huge database project. So now we're going to create a uniform data model across all these silos and create systems. So we're going to do like some data lake solution, data warehousing solution. If the goal is to do machine learning, you can do federated learning instead, and then you do this kind of locally. But you need to transform the data into something that makes sense, of course, to have a site. But for example, if you have 3 or 4 different databases that you need to read from, I mean, yeah, it's doable, of course, to write those scripts. Maybe it's easier than to get the whole organization to rally up behind a single database solution in some situations. So I can just show you what you could do. I'm not saying that you should, because it's something to think about. I will just share and clearly look what so this studio looks like this. So what we can do in this platform, like if you wanted to, you could in principle take this software and you can deploy and host that from your side to your users. And then you could like tailor it and adapt it. Because in this platform, users can come. So your researchers, they could come and they could like do projects together. And then what our software does is that it gives you like a way to, collaborate on these compute packages, to distribute them, to handle all this kind of federated stuff. What you would need to complement this with is some sort of data set registry or something that they can actually look at what data sets are available on the remote sites, and which one have adapters that make them compatible, or like at least instructions how do you develop those adapters. But in principle, then you could have like federated learning work, and then you set up clients for each of the data sets that you want to work with, and then you need a way to start some small sidecar service on compute resources able to access the data, but this can be of course solved. So I'm not saying it's trivial, but definitely it would be a way forward for you. And the advantage then is that you probably don't have to do the anonymization, because the data can't leave your premises.
Follow-up question: does this work? Like, the data here is on a separate network that is not connected with the internet. How would that work with this?
Well, we're not connected to internet. Exactly what do you mean? It's like completely offline.
Yeah.
I mean, what this requires is that, of course, there needs to be. We don't require that you open any ports in networks and stuff like that client side. We have engineered it in a way that it's like you don't have to modify anything in your firewall settings. But you need to be able to listen for compute requests in some way or another. So in that case, probably we would need to set up like a proxy server that can listen to the requests, and then you make some sort of internal. I mean, so you have to go there physically there.
Yeah, I get it. Yeah, I get it. We have something like that. We have something like that in place.
Like a Yam post or something.
Yeah. Got it. Thanks.
Cool. I feel I saw another hand before being raised, but now it's now it's gone. So Olivier.
Yeah. Hi. Sorry for the noise outside. I was just wondering a very naive question about the market for your company. I wonder if I understood correctly. Can this be applied to a situation where safety is a concern? I'm thinking about a company working with military or something like that. Is federated learning also a solution for that problem, or am I completely off?
We are not off. I mean, we are very interested in that sector. Cybersecurity, defense, dual use, because we think it's also a way to make infrastructure more resilient.
Right.
By decentralizing it, and also like it's highly security sensitive. But federated learning is an emerging technology. It's like you think of it as deep tech AI somehow. With this said, I would say, I mean, we have gone a long way with Scaleout. So we have software. We can, it's not the software that is blocking us at this point taking it to production. I would say it's like the imagination and consultancy work needed to like discussion with Gino here, like how do we actually build it. But yeah, we're very interested in those type of applications for sure. There's a lot of like vehicle potential vehicle use cases, for example.
Thank you.
And I should also say, I mean, we of course, I understand that sometimes this is not maybe the first solution you think of, but we are of course very happy to, or interested in collaboration with Codon, for example, in realizing use cases. both early or late stage. So if you see anything, don't hesitate to talk to us. And of course, if you wanted to put up some POC yourself, I mean, you can do that with our software. You can just request an account and play with it and see if you get any ideas.
Cool. Yeah.
Just as if I may, and super quick comment there, Andreas. We are actually collaborating now, Codon and Scaleout. There's a nice opportunity for it via Henrik Göthberg and Andreas.
Oh yeah, that's right.
So hopefully we can find some.
Yeah, absolutely.
Hopefully we can find some super nice cases there.
Oh, I think so. And I mean, from Scaleout perspective, we're trying to be focusing on these kind of AI cybersecurity questions. We don't really have competency so deep in particular machine learning for particular use cases. We're reasonably good at image analysis right now, but we have done less work with language, for example. So that's
Right. Thanks a lot. Very good presentation and good informative Q&A session as well. Next session will be in about a month because of Good Friday. So and then I hope to see all of you there. Invites will get sent out.